Hello everyone, my name is Aditya Pradhan and in this video tutorial I am going to explain about various FIR filters and later I will explain how we can use these filters together for a real life application. So let's get started. So first of all, what is a FIR filter? FIR stands for Finite Impulse Response. A FIR filter is a filter whose response to any finite length input is of finite duration because it settles to 0 in finite time. In this video tutorial, three different filters that we'll be talking about are the moving average filter, the first order difference filter, and the three-point central difference filter. So the first filter I will talk about is the moving average filter. The moving average filter is a simple low-pass FIR filter, commonly used for regulating an array of sample data. It takes L samples of input at time and takes the average of those to produce a single output. This is a very common FIR low-pass FIR filter and it is very regularly used by scientists for various purposes. As the length of the filter increases, the smoothness of the output increases, whereas the sharp modulation in the data are made increasingly blunt. This helps in the smoothing process. So let us see the time domain analysis. The time domain equation of the moving average filter is defined as y of n is equals to 1 by L summation I 0 to L minus 1 x n minus I. This means we are taking the average of the time samples starting from x, the present time sample, till L minus 1 samples from this input sample, and then summing them up and taking the average of 1 by L over 1 by L. Now to know the input and output characteristics of the filter and to understand the behavior, we use the Z transform method and find the transfer function of the filter. So we'll do Z transform on either side and find that y of z is equals to 1 by L summation I 0 to L minus 1 z of I x of z, where L is the window size. To find the transfer function, we'll simply divide y of z with x of z, and that should give us this 1 by L summation I 0 to L minus 1 z of I. This is the transfer function. Suppose we take our window size here as 8, then our transfer function will become 1 by 8 z to the power 8 minus 1 divided by z to the power 7 into z minus 1. Now for further analysis, we will find the poles and zeros of the system. So finding the poles will equate the h of z to infinity, and this will give us poles at only z is equal to 0. Similarly for zeros, we will equate this h of z to 0, leading to zeros at minus 1, plus minus 1, plus minus e to the power plus minus j pi by 4. Here we see that there are 7 zeros but 1 pole. We already know that a system with more zeros than poles will be an anti-causal system. That means the output value depends on future input values, which to some extent is not to some extent, which completely is not realizable in a physical world situation. So how do we counter the situation? Here you can see the pole zero plot of the transfer function that we did in MATLAB. You can see the 7 zeros on the circle over here. Closer look here at the pole. We had only one zero at the origin, at one pole at the origin, but now you can see there are 7 poles at the origin. So that means if the number of zeros are more than the number of poles than the transfer in the transfer function, then we make the number of zeros and number of poles equal by including some number of poles at the origin. That is the difference of the zeros and poles. Last time we had 7 zeros and 1 pole. So we added 6 poles at the origin and now there are 7 poles at the origin. Moving on, let us do the frequency domain analysis of this. So we'll first replace z with e to the power minus j omega in the transfer function and then find the magnitude and angle. This would give us the magnitude response and the phase response of the filter. So the magnitude response goes like 1 by 8 sine 8 omega by 2 divided by sine omega by 2. And similarly the phase response goes by e to the power minus 7j omega by 2. Now again we'll plot these on the in the MATLAB and we'll find the curves looks like this, which here is the magnitude response and here is the phase response for the moving average filter. Next, we'll implement these on a Arduino Duo board and see what we get. So here the input array has a sample size of 1000 and this is the output array. Here we have set the number of samples or the window size as L is equals to 8, and this here is exactly the same implementation as I saw, where y of n is equal to summation 1 x upon x l I is equal to 0 to l minus 1 x of n minus I divided by l. This is just the application of that converted into C algorithm. And here we have actually set the baud rate, which is very important for when you are doing anything on the Arduino board. This sets the speed of processing for the entire process. So this is what we will obtain after the filtering has been done and after we use the serial plotter in the Arduino IDE. So this here is the message signal. You can see there are a lot of noise components in this signal, but when you pass it to the moving average filter, it reduces and smoothens the curve. This is because it is a low pass filter and it will neglect the high frequency components present in these and try to smoothen the curve. Moving on. The conclusion for this is the moving average filter acts as a good low pass filter and removes the high frequency noise component from the signal. If we increase the window size of the averaging process, the cutoff frequency of the filter decreases and we get more and more smoother signals. So as we go on increasing from 8 to 16 to 24, the smoothing increases, but at the same time the cutoff filter also decreases. The next one we'll be talking about is the first order difference filter. This one is a simple high pass filter. It takes in the present input sample and the previous input sample and gives the difference of these samples as the output. We show you what this means. If we do the time domain analysis, the time domain equation looks something like this, where the output y of n is x of n, that is the present input value, minus x of n minus 1, that is the input value just before this present input value. We take the difference and find the output. Similarly, process to the moving average filter. Here we will again find the z transform on both sides and we find y of z is 1 minus z to the power minus 1 x of z, and transfer function is just the ratio of the output z transform to the input z transform, and that is 1 minus z to the power minus 1. Again we find the poles and zeros. We can see there is only one pole at z is equal to 0 and 1 0 at z is equal to 1. So this system is physically realizable. Moving on, this is what the pole 0 plot looks when we do it in MATLAB. Again, we do the frequency domain analysis of this by replacing z with e to the power minus j omega, and we see that the magnitude response is 2 sine omega by 2 and phase response is tan inverse cot omega by 2. This here is the plot of the magnitude response and the phase response. You can see the variation in the graphs. Again, we'll implement this as well on Arduino Duo board. So here also the sample size is 1000. We set the baud rate here and we do the implementation over here. You can see this is a pretty simple implementation. It is clear from the time domain equation that y of I is x of I minus x of I minus 1. Here you can see that this is the message signal and this is the output signal. You can see there is a lot of disturbance in this signal in the output that we obtain, but it is very hard to actually see any proper result. But if you look closely, you can see wherever there are the peaks, there are some distance between the signal values. You see at every peak, we can actually observe these differences at the peaks. Though it is not very large, but still it is observable. So, what do we conclude from this? First order difference filter acts as a good high pass filter. enhancing the high frequency component of the signal. Such filters can be used to highlight the peaks in signal where there is sudden transition at peaks. As I told you, we were able to achieve some different kind of signal data, output data at the peaks, and this is what it highlights. Moving on, 3-point central difference filter. This filter is very much similar to the first order difference filter. Here, instead of taking the previous time sample, we use the sample before that to calculate the output. As such, more accurate output is obtained. Let us see what this means. The time domain analysis shows that the equation goes like y of n is equals to x of n minus x of n minus 2. Here, instead of x minus 1, we have replaced it with x minus 2. That is the only difference between the previous and this filter. But there are a lot of differences in the output obtained. Here goes the transfer function for this filter. You can see the transfer function is 1 minus z to the power minus 2. Here the poles are located at z is equal to 0 only, but zeros are located at plus and minus 1. The system has two zeros and a one pole. So as I said earlier, since the difference between zeros and poles is 1, so we will add one pole at the origin to have equal number of zeros and poles and make the system physically realizable. As you can see, we have two poles at the origin and two zeros at plus 1 and minus 1. Now, the frequency domain analysis will be done by replacing z with e to the power minus j omega. And we get magnitude and phase response somewhat similar to the previous filter as well. The magnitude response is 2 sin omega and the phase response is tan inverse of cot omega. As you can see, the graph is somewhat similar. The magnitude response is a bit different, but the phase response goes somewhat similar. Now again we'll implement this as well on the Arduino Duo board. You can see the sample size is 1000 and we just replace the x of I minus 1 to x of I minus 2. You can see 3-point central difference filter does work similar to the first order difference filter, but you can see this work is quite observable. The difference in the curve is quite observable. You can see how big these portions are to enhance or show the fact that there are peaks present in these parts of the input signal. So 3-point central difference filter essentially acts as a band pass filter. It enhances frequency components of signal in particular band. Such filters can be used to highlight the high frequency components in the signal after removing the low frequency components and very high frequency noise. That's why we are very easily able to obtain better results than the first order difference filter. Moving on. So now it's time for the real-time or real-world application of these filters. So here the experiment we are doing is the smoothing of the PPG signal using combination of various FR filters. Instead of one filter, we'll be using the combination of these filters to obtain a smooth PPG signal. So what is the PPG signal? PPG signal is an optical technique for measuring the perfusion of blood in skin and tissues arterial vessels. In this experiment, we'll have sampled the PPG at 100 Hz, with the sample size being 1000. Now, due to the simplicity, accessibility, and abundance of information on cardiovascular system of an individual, this is a very pervasive topic of research within recent years. Scientists generally use PPG for a lot of calculations. But with these benefits, there are many challenges that we face, and this signal consists of various noise components such as high frequency noise, and it also has the baseline drift component. It becomes necessary to remove these noise components for error-free calculation. Let's see what the methodology will be for doing this experiment. First of all, we'll take the PPG signal and pass it through a moving average filter of window size L is equals to 8. This essentially removes high frequency noise components. After that, this new signal is passed through the first order difference filter. This will essentially remove the rest of the remaining high noise components and give us an almost noise free component or almost noise free signal. Now the only component that needs to be removed is the baseline drift component. So what is this baseline drift component? It is caused by the respiratory rate, muscle tremor, and physiological changes within the body as a response to various stimuli. This will be there because the sensors that we use are affected by these factors and we cannot stop these factors from happening. So this component always exists, and to remove this we simply use the moving average filter again, but this time we change the window size to L is equals to 800. The signal obtained now is free from the noise components and hence can be used for various purposes. So now let's see how this can be actually implemented on the Arduino Duo board. First of all, we'll consider the sample size as 1000 as I told earlier. Y of 1000 will be our output array, Z of 1000 is the first order difference filter output, and out of 1000 is the baseline drift component array. So first of all, we will set the window size as L is equals to 8 and apply the moving average filter. Here, the signal that we obtain is the signal without the high frequency part. Now we'll again pass this signal through a first order difference filter to get the still remaining peaks or the noise component parts in the signal. Z of I actually shows those parts. Now to remove the noise components, we just subtract it from our original signal. And what we obtain here is a noise free component from high frequency noise free component. Now for the baseline drift, we increase the window size to L is equals to 800 and we'll find again with the help of moving average filter the baseline drift component. Here out of I gives us the baseline drift component. Now out of I and subtracted from the Y of I array will give us the final output which is almost free from all distortions and is a very much smoothened signal. Here is the baseline drift component that we took out by applying the moving average filter with the window size L is equals to 8. Now we need to subtract this as well from the signal that has been obtained or the smoothened signal that has been obtained after high frequency noise cancellations. This is the final output that we get. Here you can see the message signal with high frequency noise and baseline drift component. And this is the final output, very much smoothened and very much ready to be used in real world applications. In this, so it is quite visible that use of successive FIR filters has smoothened the signal to a higher extent as compared to use of a single filter. We saw in the moving average filter that even there the signal was smoothened to quite a good extent, but the previous plot shows that we can have better results if we just use a combination of other filters as well. With this, we come to an end in this video tutorial. Thank you for watching.